So students, today we will take up a special problem on the absolute motion analysis. You remember that in our last class we have discussed the absolute motion analysis method for a couple of examples, and now today we will take up a special problem in our rigid body kinematics, and this is a problem which is known as rolling without slipping, or which is also termed as the ideal rolling condition. The problem on this, and these types of problem occurs quite often in our engineering analysis, and therefore we need to actually study this type of problem. So what is the problem? Let me first define the problem here. The problem is that we have a circular inwardly circular surface of radius of curvature r with center of curvature at point O, and on that surface we have a cylindrical or a sphere-like substance, cylindrical or sphere-like rigid body whose radius is of course equal to small r, which is going to be less than our this capital R. So this small r, this sphere-like or cylindrical like substance is there, and this is actually climbing up this surface in this manner, and it is climbing to this particular position, and at this instant what we need to do is to calculate the velocity of any point on the geometry. Say the point B, which is defined at a distance of rho from the center of this cylinder or the sphere-like body, and which is at an angle of beta from this initial, this fixed line. So this line is a fixed line OA, it is a fixed direction. So this angle, we call this angle is to be equal to beta, and that is how we locate the coordinates of the point B. So we need to calculate the velocity and acceleration of this point B at the position when theta is equal to 0. That means when it is here in this initial configuration, in this initial position, I need to calculate the velocity and acceleration of this point B, which is an arbitrary point on the body. By controlling these two parameters, rho and beta, in fact, you can take any point on the associated with this rigid body. That means if we consider, for example, here we have taken this rho to be less than r, right, but smaller, in fact. So it means that you can take any rho value starting from 0 to the radius smaller, and that's how you define any point from starting from the center to any point on the circumference of this body by controlling this. And we can also take the different angular positions of the point by taking this, by varying this angle beta. For example, if we try to calculate the velocity of point A, which is here, I can make beta to be equal to 0 and rho can be made to be equal to smaller. So that's how I can take different points. Even someone can take any outside point also. That means if there is a rigid body connected with this rolling sphere or cylinder, and we can take a point on that extended part of that body, and we can calculate the velocity and acceleration of that point also while this body will execute the motion. So what we do here, we actually take any general configuration of this body, and that general configuration is being defined by this particular position. When we see how this particular position can be achieved, now this is when you need to remember that when a body actually rolls over a surface, it actually executes a plane motion, in the sense that it can be described by Chesel's theorem as a combination of translational motion as well as the rotational motion. So here we can actually consider this general situation here, by just considering this, by dragging this body, by dragging this cylinder or sphere-like body on this surface and just moving it like that in such a way that this point A, it actually moves to the location A double dash, and the center C moves to the location C dash. So this is the curvilinear translational component. But in doing so, you see here, the center comes to its desired location C dash when it will be rotated by this much amount of angle. But we note that this point A has not reached its original position. So, or in the desired position, not original position, it has not come to its desired location. So, what to do? Now, according to Chesel's theorem, after giving this curvilinear translation, where by bringing the center to its desired location, now we can give a rotation to this body with respect to the point C dash. That means make the C dash as the center of rotation and rotate it by an angle such that this radial line C dash A double dash comes to its desired position, say C dash A dash. And that desired position, let us suppose that the amount of the angle, that angular rotation that we need to perform is given by the angle phi. Now, we have therefore two angles here, theta and phi. Are they correlated? The answer is yes. If we assume that the sphere or the cylinder-like substance is executing a rolling without slipping motion. How that can be done? Now, we see that while it goes from this location to this location, AA dash double dash, this arc length, that becomes equal to capital R into theta, right? And when I give the rotation, rotational motion, the rotational component of our combined motion, the rotation is taking place with respect to the point C dash, we see the A double dash has come to the location A dash, thereby it describes this arc length which is equal to R into phi. Correct? So both are the movement of the point A. And if the body executes rolling without slipping motion, it is therefore very simple to note that these two motions, these two displacements rather, should be equal. Then there will be no slipping position because the body moves translationally, and this is the way the body actually has this amount of rotational displacement. So these two must be equal, and we have r theta should be equal to small r into phi. So that is the condition for the perfect rolling motion. The displacement along the translational component and the displacement due to the rotational component, they must be equal for the point of contact. This point is the point of contact. And we have, this is the desired thing. And from here we can write phi equal to capital R by R into theta. Now you see that in doing this motion, the body is having some angular velocity because it is undergoing rotation. Let us suppose that the angular velocity of this body, let us say that this angular velocity, let us write it here clearly, the angular velocity of the body is omega. Then how we can calculate this omega? We have learned in our previous class that you need to take any reference line and then calculate the orientation of that reference line. So here we have taken this as our reference line. In fact, we have placed an inertial reference frame because we are doing absolute motion analysis. It means that we need to track the geometry as measured from the origin of a reference frame which is absolutely fixed to the ground, or so to say, which is inertial reference frame. So this is the x and y axis with its origin here coincident with the initial point of contact A. So this is where our origin is. So if we suppose that this is our origin, So we note that this line, this O and this origin, if we call that origin as, suppose we define this origin by the point P, then we see from here that this the line, that this radial line CA is making an angle 0 with respect to this reference line. So any change in the orientation, you see this, the radial line CA has come to the position C dash A dash, where you see this amount of the angle, because when you dragged it over this surface, the radial line CA has come to the location C dash A double dash, correct? And from here you need to give the rotation, and that rotation was equal to phi. So the angle between the two successive, the radial line will give me the amount of the rotation. So this is the amount of the rotation the body is suffering. So you see, therefore, the angle that this radial line will now make with this reference line is, of course, this much. That means this angle, this is the angle this radial line is making, this much angle. So how you calculate this much angle? You remember this is total equal to phi. So you see here, this angle is basically equal to, here we see, just draw this line for our purpose. So we carefully erase this phi from here. So this phi is carefully erased out from here. And we note that actually the phi is this angle. Phi is this angle. So we need to calculate, this particular angle. So how much is this angle? So that will be equal to phi. And since this angle is theta, so obviously the radial line becomes now making an angle phi minus theta with respect to this reference line, because this is the reference line and this is parallel to it. So the angle will be this much. And if we differentiate that angle, definitely that will give us the angular velocity. And this angular velocity is, of course, being given by phi dot minus theta dot, because phi minus theta, because this whole angle is phi and this angle is theta, this much angle is theta. So this total angle is phi minus theta. And if you differentiate it, you will be getting the angular velocity. But you see that you remember from here that this phi is being given by r by r theta. So I can substitute in place of phi dot and can have the expression of theta dot. Once I know theta dot, I can calculate phi dot from here. So it is pretty clear that this is how we can get the thing. Now let us track the desired point. Say you see this line CB. Okay. So when we bring this cylinder-like or the sphere-like substance, dragged it over this circumference and brought it here, you see this line comes to this position, OA has come to the position OA double dash, and you know that this CB line was making an angle beta in the anti-clockwise sense. That is how we specify this location. So the same location will be now here. So let us suppose that this is B double dash, the intermediate position. When I am dragging this over here, right, when I am dragging this geometry, so just giving the curvilinear translation, we note that the point B has come to the intermediate location B double dash, and the angle then the between C dash A double dash and C dash B double dash will be equal to beta. So we can say that here we need to write here that the angle, somewhere we write it here, the angle C dash, we can say the angle C dash and A dash, C dash A double dash, sorry, C dash A double dash B double dash. No, I'm sorry, I'm making the angle specification is incorrect. We say that it should be B double dash C dash A double dash, correct? This angle is going to be equal to how much? This angle is going to be equal to beta, correct? Now but this is the intermediate position of the point B, which is here. So in order to have the final position, what I have done here, after dragging this, at this position, we have given a rotation to this body with respect to the point C dash. As a result, this radial line C dash B double dash has traversed in the clockwise direction to come and reach the position C dash B dash. And quite naturally, we can say the angle B double dash C dash B dash. That means we can say here the angle B double dash C dash B dash, where B dash is the final location, is obviously equal to phi, the angle of rotation that we have given. Okay, so you see this B dash comes to, therefore C dash B dash is the final position of this radial line CB because of all these rotations. So let us now track the coordinates of this point B dash in order to find out the velocity of the point B. But we need to first find out the velocity at the general configuration of this point, and then we can come to this special initial configuration of the geometry. So what we need to do, we need to express the coordinates of this B dash with respect to this inertial reference frame with P as its origin. So now, in order to calculate the x coordinate of this point, what we do, we just take a perpendicular here and we note that this is our xb dash. So this xb dash, how we can calculate? Now obviously this xb dash will consist of the coordinate location of this center c dash, which is this distance xc dash, that is the perpendicular distance of c dash from this vertical line. So this is giving me the coordinates of x coordinate of the point c dash, correct? So we can therefore say that the xb dash, that will consist of this xc dash plus this horizontal, this distance, that means this distance. Now in order to calculate this distance, how we can calculate it? It's very simple. You need to just find out the angle this c dash b dash is making with respect to this vertical line. So that means this red arrow, how much is this angle? So you can very simply see that this much angle is theta. That means when you are measuring, you come to this line, this much angle is theta. So to it you need to add this remaining angle here. So how much is this remaining angle? From here you see this is altogether it is beta, altogether it is beta here as it is shown, and then we have this backtrack angle due to rotation is phi. So naturally therefore the total angle this c dash b dash is making with respect to the vertical is this theta plus this is beta minus phi, correct? So therefore this coordinate, this distance will be equal to how much? This c dash b dash sine of this angle, that means sine of theta plus beta minus phi. So therefore I can write this and can say that xb dash will be equal to, now xc dash, this is xc dash, this is actually equal to xc dash, I am explaining it little later, plus it is rho into sine of theta plus beta minus phi. Now how we are going to calculate xc dash? Now that is simple. First calculate this OC dash. So OC dash is how much? OC dash is going to be equal to OC definitely, and that is equal to capital R minus small r. So this distance OC dash is capital R minus small r. Right, and this angle is theta. So quite naturally this much distance, that means this much distance, that means xc dash, correct? So this xc dash will be equal to OC dash into sine of theta. So ultimately we see that xb dash is equal to OC dash sine of theta plus rho into sine of theta plus beta minus phi. And remember that OC dash is basically equal to OC and it is equal to capital R minus small r. So if I substitute it into the final expression, what I find from here that xb dash becomes velocity and acceleration needs to be calculated by simply differentiating this expression, remembering the fact that as time passes, theta is changing, as also phi is changing, but your beta, rho and other things are all constants. So remembering that, we just differentiate first this expression to get the x component of the velocity of the point b dash. Because you have x b dash, y b dash both, it means pretty clearly that your point b dash is having both the x and y components of velocity. So I therefore have dx b dash dt. That means I differentiate this equation with respect to time, and I get capital R minus small r into cos theta into theta dot, right? Then plus it is rho cos theta plus beta minus phi. Remembering beta is constant, it is theta dot minus phi dot. Now you see theta dot, r minus r theta dot. Now you see here, r minus r theta dot is omega into r. So in place of this two, r minus r into theta dot, we can write omega r and then cos theta comes. Note that phi dot, theta dot minus phi dot is basically equal to minus omega. So I put minus omega. So it becomes minus rho omega cos theta plus beta minus phi, and that definitely will give me the x component of the velocity of the point b prime. In order to calculate the y component of the velocity of the point b prime, what we need to do, you need to differentiate this expression with respect to time. So if you differentiate this expression, before going to differentiate that, let me complete this. When we have found the velocity, x component velocity, we can further differentiate this expression to calculate the acceleration, because we need to calculate acceleration also. So x component acceleration can be calculated by differentiating this expression, remembering that your omega can vary with time. So it will be the differentiation omega dot r cos theta minus omega r theta dot sin theta minus rho omega dot cos theta plus beta minus phi. Then it will be rho omega plus sin theta plus beta minus phi into theta dot minus phi dot as usual. Now you substitute in place of theta dot the expression. You remember theta dot is omega r by capital R minus small r. So if you substitute all these expressions and remembering theta dot minus phi dot is minus omega, you get this is your desired expression for the acceleration for the point b dash, which is pretty complicated one and difficult to explain, but we'll come and try to explain these equations little later. So once these are the x component of velocity and acceleration has been found, now we do the same procedure for finding out the y component of velocity and acceleration. Now we have to differentiate this expression with respect to time. And if you differentiate, I think it doesn't need any explanation that if you differentiate, the ultimate expression turns out to be as omega r sin theta minus rho omega into sine of theta plus beta minus phi. In this process, we have followed the same sequence of substitution and the differentiation. Again, if you differentiate this, you will be getting the acceleration for the point at b dash, and do the algebraic simplification. That means replace this expression for theta dot and replace this expression for theta dot minus phi dot will lead you the ultimate expression for your acceleration. So all these underlined expressions, green underlines indicating the velocity components, blue underlines represent the acceleration components for the point b dash only. But you remember that our problem is not to find out these velocities for the point b dash. We are to find out the velocity and acceleration for the point b, and that is where in the initial geometrical configuration. So how we will be dragging this configuration from the present one to this initial one? Just by making this theta equal to 0. And you remember, if theta equal to 0, your phi is also 0. So you need to make double substitution. that to arrive at the initial geometry, you need to substitute this double substitution. That means you need to put theta and phi both to be 0 in the above expressions. So if you do it, you see Vxb turns out to be as this was Vxb dash. So when I am putting theta and phi both to be equal to 0, b dash comes to the location B. So therefore Vxb, now instead of b dash I am writing it the point B, that will be the x component velocity, that turns out to be as omega r minus rho omega cos beta, and that is if you take omega whole into r minus rho cos beta. And similarly, if you come to this, put theta equal to 0 and phi equal to 0, will make you the velocity of y component of the point B to be equal to minus rho omega sine beta. We said that why we took the point B, because we said in the onset that the parameter rho and beta, this actually defines all possible points on this body. Suppose if I am trying to calculate the velocity of point A at the initial configuration here at this point, if I try to calculate the velocity at this point of the point A, what will be the velocity of this point A? We notice from here that at this initial configuration, if I put rho to be equal to r, in order to get the point A from point B, what you need to do is you need to make double substitution. That means rho to be equal to r and beta to be equal to 0. That's how you will come from the point B to the point A. Correct? So what we need to do therefore, now here what we need to do therefore is something like this. We can come to that situation. That means we can put theta equal to 0 and phi equal to 0 both in this expression, and you will notice that the velocity of the point A will be equal to simply 0. Similarly, you will be able to get the velocity, y component of velocity for the point A to be equal to 0, which will undertake the situation VA to be equal to 0. And this is most important observation. It is because that we have said that the object is, in this case, the cylinder or the sphere-like rigid body is executing a rolling without slipping motion over this static surface. So since there is a static surface and the point of contact is a coincident point, means it is a common point between these two bodies, rolling without slipping means that there should not be any relative motion or there should not be any slipping action here. Rolling without slipping. So without slipping means that this point A, there should not be any variation in the magnitude of the velocity when I am considering A to be the part of this outer circular surface and when I am considering it to be the part of this rolling body. Since when it is belonging to this outer surface, since it is static, its velocity must be 0. So it means that over this also its velocity must be equal to 0. Now in this geometry, when it comes to the general geometry, and in this geometry, in order to bring the point B dash, in order to bring the point B dash to the point A dash, what you need to do is simple, that you need to make this angle, that means this angle, that means your phi minus beta, this angle was phi minus beta. Remember, this angle is beta minus phi, so this angle was beta minus phi. So what you need to do, you need to make this beta minus phi, this angle to be equal to 0, and to make this rho to be equal to small r. So then you will be coming from B double dash to the location A double dash. So you see beta minus phi, if you come to this position, so beta minus phi to be equal to 0 and your rho to be equal to r, you see it becomes omega r cos theta minus omega r cos theta, and the result to be equal to 0. So it means and you can verify it here as well for the y component of the velocity also. You see beta minus phi equal to 0 and rho to be equal to smaller. Again, you will find that the velocity of the point A dash, that means the final point of contact, that means A double dash, sorry, A double dash, this point of contact, here also the velocity must be A double dash point, its velocity must also be 0. So it means that the point of contact at any geometric configuration, here this point of contact, its velocity must be equal to 0, and that is in line with the requirement that our body is executing rolling without slipping condition. So you see, therefore, this is the most general expressions. I mean to say, this expression and this expression, if I call the expressions, name them as 1 and suppose I call it as 3, I call this acceleration expression as 2 and this expression as 4. So you see, the expression 1 and 3 will give us the velocity of any point at any arbitrary geometric configuration. So by making suitable adjustments regarding your positional coordinates theta and phi, here actually theta and phi, we have used theta and phi. In fact, we can replace any one of them by the other because of this relation, that r theta is equal to, remember this relation. So any one angle can be replaced by the other. So if we desire, we can solely express it in terms of the angle theta, or we can express it in terms of angle phi. So actually, although there are two angles we are using here as our coordinates, but they can be brought down to any one coordinate angle. So either it can be made a function of theta, because beta is constant, so either you can make this as a function of theta totally, or you can make the whole expression as a function of phi. Because here theta is present, it will be desirable that this angle is also converted to the similar transformation in terms of the angle theta. So therefore, you see that the 1 and 3 will give me the velocity of the point as the function of the angular displacement theta in the problem. Now this is regarding the velocity. Now how we can calculate the acceleration of the point A, acceleration of the point B in initial configuration? So we see again we can write, again for acceleration we can say thus, we can write it like that ax, that means the x component of the acceleration of the point B will be what? So you see here, we invoke our equation 2 and substitute theta equal to 0 and phi equal to 0 in the expression. So you see, it becomes omega dot r, theta equal to 0 means it will be cos 1, cos 0 means 1. So it will be therefore omega dot into r. So we write it like that. It is omega dot into r. And then we have this expression. It does not exist because theta we are making it to be equal to 0. Then we have minus rho omega dot, theta and phi both 0. So it is minus rho omega dot cos beta. So we can say this is minus rho omega dot, we can say this is minus rho omega dot into cos beta. So both omega dot terms are there. That is one thing that we can further analyze it. And then theta and phi both 0. So it becomes minus rho omega square sine beta. So we can write this to be equal to minus rho omega square sine beta. So you see, the acceleration has two components. Taking omega dot common, we can write this is r minus rho cos beta, this into omega dot, and then we have minus rho omega square sine beta. Now people often make mistake, they differentiate these expressions to find it out. Then it will be wrong, because these are instantaneous expressions. They cannot be differentiated. you need to differentiate an expression which is generally function of time. Now this is not a function of time expression, because you see every parameter here is constant. So you cannot differentiate this expression to get the acceleration. So this is a common mistake people often make. Now this is for the x component of acceleration that we are getting for the point B at the initial configuration. Similarly, you have AYB, that means the y component of acceleration for point B. If you put theta equal to 0, the first term does not exist. Then we have this term, that is omega square, we can say omega square r square by capital R minus small r. This expression is there. Theta is 0 means it is 1. Then it becomes minus rho omega dot. So we can say this is minus rho omega dot into sine of beta. We can put this is minus sine of beta, and then you have plus rho omega square into cos of beta. Correct? So this will be therefore the expressions for the accelerations. So these are your desired expressions for accelerations of point B in the initial configuration. Now again, if we look at that point of contact, because we said that the point of contact is a very special point in this rolling motion problem. So for point of contact, we can write, therefore, for the point of contact, we can go for any geometrical configuration, either initial or the general one. We take the initial configuration, correct? And I will ask you to verify it for the general configuration. For point of contact at initial situation, at initial configuration, we can say at initial configuration, we need to calculate the acceleration of point A. So we put AX A. What will be the consideration? You remember, we need to put R rho equal to R, double substitution, and beta equal to 0. Right? That's how you are getting the point of contact. So here, if you put rho equal to R and beta equal to 0, then you find that this is beta equal to 0 means this becomes 1. This R and rho being equal, so this term will not exist. And rho omega square beta being equal to 0, this will become simply 0. So it means that the point A does not have any horizontal component of acceleration when it is at the initial configuration. Now you see what will be the y component of acceleration. Is it also 0? Because we have seen that both the components of velocities were 0. Let's see whether the y component of the acceleration for the point of contact A, that means whether it is 0 or not. Correct? So if I put this here, I find that if I put beta equal to 0 in this case, I note that it becomes equal to omega square r square divided by r minus small r, and then it becomes plus, because this component is not there. So even if the body is having angular acceleration, it is not being reflected here. That's very interesting, that your omega dot term does not survive, and then you have this is r omega square and cos beta is 1. So it is definitely not equal to 0. So unlike the velocity component, you see the acceleration component is not vanishing. So it means that the point A is having some acceleration, and that is in the upward direction because it is turning out to be plus. Now you see till now it is plus. So omega square r taking common, so I can take this omega square r from here common. So it becomes r minus capital R minus small r plus 1. So it means that the acceleration, so it gives us the fact that AYA, that means the acceleration along the y direction at the point of contact, it's becoming equal to how much? This r minus r. So you see this r and will get cancelled, and it becomes equal to, that's very important to understand, it is becoming equal to omega square rr by capital R minus small r. And this component of acceleration, that is very important to note, that it is turning out to be in the upward direction. So coming back to our initial geometry, if you look at this initial geometry, so this is the initial geometry, I notice here that the velocity of this point must be 0 as it should be, and I found that the horizontal component of acceleration is also 0 at this point. However, this point is having acceleration towards the center, right? You remember this was the case we dealt with in our system of rigid bodies. We have three conditions. Out of that, the third condition was when we can write summation ma equal to h bar a relative dot. If you remember that our lecture, in case of system of particles, we noted that when point A will be having acceleration towards the center of mass of the body. So if you assume here your sphere to be homogeneous or your cylinder to be homogeneous, this center, geometric center and center of mass will coincide. And then you see the point A will satisfy that third condition, that it is having acceleration towards the center of mass. Of course, for that you need to make this rigid body as a homogeneous one. If it is non-homogeneous, even then its acceleration will be directed towards the center, but it will not comply with that third requirement because your center of mass will not be here. If the body is non-homogeneous, your center of mass will not coincide with the geometric center of your body. So in that case, the third condition will not hold good, but you need to remember your acceleration will be always directed towards the center of this rigid body. So this is a very, very important observation. And I like to invite you to observe what will be the case of acceleration of a double dash point. What are the components of the acceleration of a double dash point at this general configuration? Try at your home to find out what should be your acceleration components. Now the beauty of this, why we chosen this parametric definition of the point B, I hope that it is now pretty clear to you that by suitably varying your beta and rho, you can, choose different points on your cylinder or the sphere-like substance within the body, outside the body, or on the body. You can take any point by varying, by changing your rho, and by varying your beta, the angle, you can come and track and you can find out the acceleration. For example, here we have found the acceleration of point A. Somebody can find what should be acceleration at the topmost point here at this initial configuration. So all these, any geometry you can think of, you can solve. And another interesting thing is to, ultimately track the motion of point C or the center. See, in order to get the point C from our parametric definition, so what we note for point C or the center, motion of the center, so if we now focus on to consider the motion of the center, so in order to track down it, center C, what should be our, the substitution in our parametric definition? So it is pretty clear that you need to put rho equal to simply 0. So just one substitution is enough to bring the point B to the center of the body. So in your above expressions, so whatever expressions you have found for your velocity, for your accelerations, etc. Suppose this was the velocity expression initially, correct? So if you come to the initial condition, so in the initial position, So we can say in the initial position where we have placed our coordinates, in the initial position we can see that if you make rho to be equal to 0, correct? So what should be the acceleration of the velocity of the center? So you see from here that your velocity of the center point will be, we can write it this way, so it will be Vxc, the velocity of the center, that will be equal to, by putting this rho to be 0 means that it should be equal to omega into r. So it is equal to omega into r. That is the thing that you are getting. So it is equal to omega into r, correct? So omega into r is the velocity and the x component, and what should be the y component velocity? Now it should be 0 because the center is moving, so in that way, so it should be equal to 0. So it means from here that your body is basically having, so at this point the center point is having just a velocity towards right. It has having only the x component of velocity, and that is equal to omega into r being the radius of the body, omega r. Simple equation of your it's a very famous equation, the equation which actually establishes the relationship between angular motion and the translational motion. So that omega into r, so that should be your velocity of the center. And what about your acceleration? So again, if you come and put in this expression your expressions for acceleration, so you see that your axc, that turns out to be, because you are dealing with rho to be equal to 0, so cos beta term, it doesn't matter, so it will not be there. So it will be omega dot r, so axc will be equal to omega dot r, and this term will not survive because you have put rho to be equal to 0. So that is axc omega dot r, and your ayc, that means the acceleration of the center in the y direction, it will be here in this expression. If you substitute everything, that means you put your rho to be equal to 0, so these two expressions will not be there, so it will be simply equal to ayc, that will be equal to how much? That will be equal to your omega square r square. So you get, this is omega square r square by capital R minus small r. So that will be going to be your acceleration for the center of mass center of the cylinder like or the sphere like substance. So it is equal to omega square r square by capital R minus small r. That will be going to be our y component of acceleration for this entire problem. If we put in this expression, these are your general expressions, correct? General expressions in the case, and we substitute in it here at the initial position. So this is how you are getting, and we get what should be our acceleration for the center of the cylinder like substance or the sphere like substance. So students, therefore we have dealt with a very important a problem. It's a very important problem that we have discussed in this case, that is actually the what is termed as the what is called as the rolling without slipping over this inwardly curved surface. Now I will give as home assignment, there will be two problems will be given to you. In this case, the first problem will that if you change this from the inwardly curved surface to outwardly curved surface, what will be your general expressions for the things that we have derived? That is number one. That means you need to repeat this problem considering this to be, instead of an inwardly curved surface, you now consider this to be an outwardly curved surface. That is assignment number 1. And another homework that we can give, that if we make this surface to be flat, that means if we make it a totally a straight line, and then consider rolling without slipping for the other things remaining the same, repeat the same work for the case when you are having this surface to be really a flat line. Now there is an interesting thing we need to note, that if this body, if suppose if this is a cylinder and this is, this arc length is there, if we allow this to rotate without slipping, it will actually generate a curve. If you consider the locus of any point here, suppose if you try to consider the locus of the point of contact, because your point of contact is changing. Say this point A, right now it has come to A dash when it has gone by an angle theta. And then if you consider the whole such variation, if you consider this to be a complete, I have taken it to be a part of a circle, but if you consider it to be a completely a circle and allow this cylinder like substance or the sphere like substance to roll without slipping over the entire surface, what will be the locus of this point A? And the locus here will be termed as the hypocycloid. And the locus of any inside point, that means if it is inside here, or it can be outside also, if it is inside or outside, then the corresponding locus is known as the hypotrochoid. Let us see how these two curves will look like. We have and reanimated it in our Excel file, and we can show how this hypocycloid or the hypotrochoid can look like. So this is the problem. This is the this is the whole. We need to focus on to this graph. So you see, this is the whole outer circle indicates that bigger circular path, and this blue curve here, it indicates the locus of the point of contact. So you see, this is your rolling body. I mean, it can be a cylinder or it can be a sphere. So this is a rolling body. This rolling body is rolling over this, it rolls over like that, correct? So we can generate this curve and we get, the blue cusps. These are called cusps. So these blue cusps are actually, defining your hypocycloid. And the brownish type of curve that we have shown here is actually the hypotrochoid. That means the locus of any inside point within the cylinder or the sphere-like substance as this rolls over this bigger circle. So we see that we can generate all these things and can find out these interesting curves. And that's why we consider this to be a special problem which we need to discuss with you. And I hope that you have understood the basic physics of the motion, and I will ask you to do the sums, whatever I have mentioned here at your home to verify and come out with the results. And with this, I come to an end of today's special discussion, and I hope you have understood this, and thanks for watching my video.